So for each of the following infinite series, state whether the series is geometric. If it is geometric, the value of the common ratio, and then find its sum. And there's one series on this page whose convergence or divergence is still a mystery. Okay, so I have to analyze, is there some number that I multiply by, a constant number, to get from one term to the next? So the easiest one to check is the first one. 1 times what is a half? It's times a half. And a half times a half is a fourth, times a half is an eighth, so this is geometric. And the first term in the series is 1, and the multiplier x is 1/2. Because that x value is between -1 and 1, it converges. And it converges to a over 1 minus x, so 1 over 1 minus a half. That's 1 over 1/2, which is 2. Okay, 2 plus 6 plus 18 plus 54. Is this geometric? Well, let's see. 2 times what gives you 6? Times 3. And 6 times 3 is 18, times 3 is 54. So yes, this is geometric. And the first term in the series, a, is 2. The constant multiplier x is 3. But that constant multiplier of 3 is not between -1 and 1, so this does not diverge. So this is NA, right? The sum is not finite. Okay, part C, we want to write out at least the first 4 terms on this one. So I'm going to plug in n equals 1, and I get 1 minus 1 is 0, 0 cubed is 0. Now I plug in n equals 2. 2 minus 1 is 1, 1 cubed is 1. Now plug in a 3. 3 minus 1 is 2, 2 cubed is 8. Now I'm going to plug in a 4. 4 minus 1 is 3, 3 cubed is 27. And maybe I'll do one more. 5 minus 1 is 4, 4 cubed is 64. Is there a constant multiplier to get from one term to the next? So 0 times what is 1? Nothing. 1 times what is 8? 8 times 8 is not 27, so this does not have a common multiplier. Not geometric. Does it converge? It doesn't seem like it, because my terms, I'm just adding larger and larger numbers, so this sum is just going to approach infinity. It's going to get bigger and bigger and bigger unboundedly. So this does not converge, so the sum is not applicable. Okay, write at least the first 4 terms on this one. So 3 times 3/4 to the n. So I'm starting with n equals 0 here. So when I plug 0 in for n, I get 3 times 1, which is 3. Then when I plug a 1 in for n, I get 3 times 3/4, which is 9/4. Then I plug a 2 in for n, and I get 3 times 9/16, which is 27/16. And one more, I'm going to plug in a 4 for n. So get 81 over, that's not right. Okay, so this is over 256. No, that's 4 cubed, that's 64. 81 over 64 plus dot, dot, dot. Okay. So is this geometric? Is there a constant multiplier? So 3 times what gives you 9/4? 3/4. 9/4 times 3/4 is 27/16 times 3/4 is 81 over 64. So yes, there is a constant multiplier. This is geometric. The first value in the series is 3. The constant multiplier is 3/4. And because that constant multiplier is between -1 and 1, yes, it converges. And it converges to the first term, 3, over 1 minus the multiplier. So that's 3 over 1/4, which is 12. Okay, so the next series is the sum of 1 over n from n equals 1 to infinity. So the first 4 terms, I have 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus dot, dot, dot. Okay, is there a constant multiplier? So 1 times what is a half? A half. If I multiply by a half again, do I get the next term? A half times a half is a fourth, not a third. So this is not geometric. So NA, NA. Does it converge? I don't know. I don't have any way of knowing that yet. Okay, to write 0.19191919 repeating forever as a fraction, we first rewrite it as 0.19 plus 0.0019 plus 0.000019, etc. And we recognize that this is geometric. Okay, so what do you multiply 0.19 by to make 0.019? 0.0019? 0.01. That would move the decimal place 2 to the left. And if you multiply by 0.01 again, you get the next number in the list, and on and on. So the infinite sum, which is a over 1 minus x, a is the first term in the list, 0.19. 1 minus x is the multiplier, 0.01. So this is 0.19 over 0.99. Multiply the top and bottom of that fraction by 100, and you get 19 over 99. We can use this same approach to figure out the fraction that 0.9 repeating forever represents. So 0.9 repeating forever could be 0.9 plus 0.09 plus 0.009 plus 0.0009 plus dot, dot, dot. So I have a constant multiplier. I'm multiplying by 0.1. That moves the decimal point 1 to the left. So 0.9 times 0.1 is 0.09, times 0.1 is 0.009, etc. So my infinite sum, a over 1 minus x, first term in the list is 0.9. 1 minus the multiplier of 0.1. So this is 0.9 over 0.9. Multiply top and bottom by 10, you get 9 over 9, which is 1. So 0.9 repeating forever as a fraction is actually 1. All right, let's say a patient is injected each day at the same time with 30 units of a certain drug. Suppose the drug is eliminated from the body exponentially, with the half-life of the amount from any single injection being 1 day. So how much drug from a single injection, we're just talking about a single injection, not the sum of all the daily injections, after 1 day. So a single injection begins with 30 units of the drug, and half remains at the end of each day. So we multiply by a half for however many days have passed. So that's the amount left from a single injection after T days. All right, we're going to write a series that represents the total amount of drug in the body after 10 days. I'm going to change this problem to be a specific number of days, which means the 11th injection has just been administered. Okay, so I need to add up all the amounts of drug from each injection. So the 11th injection was just administered, so it has 30 units, was just put into the body. Okay, so I have to add how much is left over from yesterday's injection. So I would have 30 units times 1/2, because only half of it remains after a day. And then from 2 days ago, I was given 30 units of the drug, and it's been decaying for 2 days, so I multiply it by a half twice. Half of it goes away each day. So I'm going to keep doing this. 30 times a half that it's decayed for 3 days. And then the last term here is going to be 30 times 1/2 to the 10th, decayed for 10 days on the 11th day. So if I put this in summation notation, I'm going to sum. Every term looks like 30 times 1/2 to an exponent to the n. And I want my first exponent to be a 0, because the second one is a 1. So I need to start at n equals 0 and go to 10. That would give me 11 terms that I wrote out above. Okay, so to find the sum of the finite series from B, I need the formula for the finite series, finite geometric series. All right, that formula, S sub n, is A times 1 minus x to the n over 1 minus x. And n is the number of terms. So in this case, it's 11. A is the first term in the list. So S sub 11, sum of the first 11 terms. The first term in the list is 30. Then I'm going to do 1 minus, x is the multiplier, which is 1/2 in this case, to the n, which is 11 terms, over 1 minus x. So I'll get a calculator to help me with this. So 1 minus 1/2 to the 11th times 30 divided by 1/2. It's 149.93 units. Okay, I just realized I made a little mistake here. I divided by 0.2 instead of 0.5. So I'm going to take that 29.98 number, and I need to divide by 0.5, not 0.2. So that comes out to 59.97 units of the drug after 11 days. Okay, if this treatment continued indefinitely, what would happen to the amount of drug in the patient's body at each injection time? So I want to look at the infinite sum, right? When I add up the sum from n equals 0 to infinity, instead of stopping after 11 injections, of 30 times 1/2 to the n. And that is A over 1 minus x. A is the first number in the series, 1 minus the multiplier, which is 1/2. So 30 divided by 1/2 is 60. So there would eventually be 60 units in the body in the long run. You've won the lottery, and the lottery prize is quoted as $1.5 million, but this amount will be paid out in equal annual installments over 30 years, with the first check arriving today and another check arriving each year until 29 years from today, so for a total of 30 checks. Or if you want the money up front, you'll get a check for $800,000 today with no further payments. So assuming you can earn 5% annual interest on your winnings, compounded continuously, ignore the effects of taxes and inflation, we want to compare these two options. Should we take the annuity or should we take the lump sum? So first we need to figure out how much these checks are going to be for. So I have to take $1.5 million and divide by 30 checks. $1,500,000 divided by 30 is $50,000. Okay, so each check is going to be $50,000. And the present value of the first check is $50,000. You're getting a check for $50,000 today. Its value today is $50,000. So my first check has a present value of $50,000. Now my second check is also a check for $50,000, but I'm not going to get it for a year. which means that its present value is less than $50,000. Because if they gave me money today, I could invest it for a year and let it grow to $50,000. So the present value of $50,000 is something smaller than $50,000. And the way we calculate it is this formula that present value is future value times e to the negative RT. So my future value is $50,000 because the check is going to be written for $50,000 in the future. And then to bring that back to the present value, I multiply times e to the negative 0.05. And then the amount of time is 1 year. I have to go back in time 1 year. So that is going to give me some amount that's smaller than $50,000. Let's just see what it is. So 50,000 times e to the 0.05. Negative 0.05. So that gives me about $47,561. So they could give me $47,561 today. I would invest it and let it grow to $50,000 a year from now, or I could just wait and they give me $50,000 a year from now. So that's what the present value means. They're going to give me $50,000 in a year. That's equivalent to giving me $47,561 today. Okay, so the third check, its present value, take its future value, is just $50,000, and bring it back in time 2 years. Okay, and I have to keep doing this for 30 total checks. So my first check has no exponent. My last check is going to be 29 years from now. So I should have put a ... there. $50,000 times e to the negative 0.05 times 29 years. So this is the present value of all 30 checks. So this is the first check, present value of the second check, present value of the third check. This is the present value of the last check. We add them all together, and that's the present value of all 30 checks. Find the sum of the finite series from B. Which option has the higher present value? Okay, so the sum of the finite series from B. So let's write it out again. Okay, this is geometric. My constant multiplier is e to the negative 0.05. What do you multiply 50,000 by to get 50,000 e to the negative 0.05? E to the negative 0.05. And that works if you keep multiplying by e to the negative 0.05. So my first term in the list is 50,000. My constant multiplier is e to the negative 0.05. So my and n is 30. I have 30 terms in this list, 30 checks total. So my sum over 30 checks is a times 1 minus x to the n over 1 minus x. So 50,000 times 1 minus e to the negative 0.05 to the n, which is 30, all over 1 minus e to the negative 0.05. All right, so I'll just put this all in a calculator. Let's see, I'm going to do e to the negative 0.05 first. Just hit enter. And then I'm going to raise that to the 30th. And 1 minus that. And then times 50,000. And then divided by, we'll do the whole denominator at once here, 1 minus e to the negative 0.05. And I get about $796,453.27. So that is the present value of all of the checks, which means I should choose the $800,000 today. $800,000 today is more than the present value of the annuity, so choose the $800,000. Okay, last little thing here. Suppose that the $50,000 checks just keep coming forever, to yourself, to your heirs, to their heirs. Would the present value be infinite? And if not, what would it be? So now I'm going to be adding up all my terms. Each term looks like $50,000 times e to the negative 0.05 times the number of years that the check comes in the future. And I'm adding up all these checks from n equals 0 to infinity now. So my sum is a over 1 minus x. My first term is 50,000 over 1 minus my multiplier, which is e to the negative 0.05. Let's see what that comes out to. $1,025,208. $0.32. So it is not an infinite amount of money. Getting a check for $50,000 every year from now till infinity is only worth about a little over $1 million. That's weird. Feels a little counterintuitive, but if you think about it, like 10,000 years from now, $50,000 it would be worth practically nothing probably because of inflation, etc. So $50,000 way, way, way in the future is worth so little that your checks for $50,000 are not even really changing the value of the money that you have received.